Hey PCH, so today I want to start getting a little bit more into evaluating limits of functions algebraically. So far we've talked about evaluating limits from graphs and from tables, but we're not always going to have those things available to us. And so we need to be able to look at questions like A and B, where they give us the actual function, and then find the limit as x approaches some value of that function algebraically. And so we're going to start by doing that of piecewise functions, and then get into much more detail in our next lesson. And so when I say piecewise functions, we've actually been working with these a lot ever since we started AP Calculus. And this is an example. What we notice and what is true about piecewise functions is that different parts of our domain are described or defined by different types of functions. So for example, like we notice from -9 to -5, this part of like this piecewise function is a line, whereas over here from like 4 to 9, there's a curve here. This is not a line. And over here we might have like an absolute value type deal. We have different pieces being combined together to form our piecewise function. And so if we are looking at this example here, we're looking at letter A. We're trying to evaluate the limit as x approaches 1 of g of x, and g of x is a piecewise function. And we see that here, right? For x values that are greater than 1, our piecewise is being defined by this top chunk, x cubed plus 1. And for x values or parts of our domain that are less than or equal to 1, our function's being defined by x plus 1. Normally, when they're asking you to evaluate the limit of a piecewise function, they're going to be asking you to evaluate at an x value that is where you have a split. And like we see that here. As x approaches 1, that is where the different parts of our piecewise are different. And we can see why they might ask us that if we go back to the warm-up. Because if we're looking at, for example, x equals -5, well, from the left, we're looking at this part of our piecewise, and from the right, up here, we're coming from way up here, like nowhere even close. And there's this big jump in our graph at -5. And so that is going to be kind of what we're trying to figure out. Hey, thinking about evaluating the limit of this, is there going to be a gap so that the two-sided limit does not exist? Or do the pieces of our piecewise line up right, and we do have a limit that exists? But the key part with the piecewise is making sure you understand like which piece of your piecewise you're using for what limit. As we go back to this example, in order to know that the two-sided limit exists, we talked about on day 1 the limit existence theorem that says the two-sided limit exists if and only if the two one-sided limits exist and are equal to each other. And so, in order to evaluate this limit of this piecewise function, we need to see, hey, what is the limit as x approaches 1 from the left? What is the limit as x approaches 1 from the right? And are they the same? If so, we have our answer. If they are different, then our limit does not exist. When I'm setting up my one-sided limits, again, it's really important that I'm referring to the correct piece of my piecewise function. For example, this first limit as we approach 1 from the left, I want to make sure that I am including the part of my piecewise that represents x values that are to the left or less than 1, which in this case is x plus 1. And so that's why I put that here. In the same way, for x values to the right of 1, those are going to be defined by x cubed plus 1. All right. And so, when we are evaluating limit algebraically, we will talk much more about this in our next lesson, and you'll see different examples that get a little bit more complicated, but very generally, and all that we'll see today with these piecewise limits is we can evaluate a limit algebraically by using direct substitution. For example, when I'm looking at this first limit, I can plug in this value 1 in for x and evaluate my limit that way. Well, 1 plus 1 is 2. That's going to be the value of the limit as x approaches 1 from the left of this function. Same thing if I'm looking for the limit from the right. Plug in 1 for x, I get 1 cubed, which is just 1, plus 1 equals 2. Well, my two one-sided limits are equal to each other, which means the limit as x approaches 1 of g of x exists, and it is equal to 2 as well. Fantastic. Let's do one more example together. Okay, the limit as x approaches 2 of h of x. Again, we notice that I'm evaluating the limit as x approaches 2, and that is where I have a split in this piecewise function. And so, when I am evaluating the left and right-sided limits of this function as x approaches 2, I want you to tell me what is going to be the function that I'm looking at for my left-sided limit. Yeah, as I'm looking for x values that are less than 2, that are to the left of 2, that means I'm looking at this top part or piece of my piecewise function. And I've written that here. And therefore, as I'm looking as x approaches 2 from the right, I'm going to use the other piece of my piecewise function. All right, now we can use direct substitution. So when I plug in 2 into my first limit here, so 2 squared is going to be 4, so equals 4. Minus 4 times 2, so minus 8 plus 7. Looks like that's going to give me, what, positive 3. And then if I do the same thing down here for my second limit from the right, negative 2 squared is 4, so it's going to be negative 4. Plus 4 times 2 is plus 8, minus 1. 8 minus 5 is also 3. Folks, our limit exists. The limit as x approaches 2 of, what is it, h of x, I think? Yeah, h of x does exist because my one-sided limits are equal to each other, and it is 3. All right, I want to do one more example with you, an example where my one-sided limits don't exist, just so we do one together and you see what I'm talking about. We'll do more practice tomorrow, or like whenever we have class again, of course. But let's go ahead and look at example E. The limit as x approaches 0, so I need the limit as x approaches 0 from the left, the limit as x approaches 0 from the right. If I'm looking for less than 0, that's going to be to the left, so e to the 2x. It's going to be up here for my left-hand limit, and x times e to the x will be my right-hand limit. And when I plug in 0, I get e to the 2 times 0. Whoops, that looks a little funky. Which just gives me e to the 0. Anything to the 0 power is 1, so my left-handed limit is 1. Let's go ahead and do the same for my right-sided limit. Plug in 0 for x, 0 times e to the 0 power. Well, anything times 0 equals 0. So in this case, my left-handed limit does not equal my right-handed limit, which means this two-sided limit, as x approaches 0 of f of x, does not exist. Awesome. That is all I need from you. Have a great day. See you later.